Hi everyone, I'm Somayeh. I'll talk about our IEEE transactions on robotics paper applications of spiking neural networks in visual place recognition. This work is a collaboration with Michael Milford and Tobias Fischer at the KT Center for Robotics. The motivation behind our work is the remarkable navigational capabilities of animals, especially those with relatively small brains navigating large unknown environments. For example, a tiny bee can travel hundreds of meters and effectively find its way back home while using very little energy. So, how can we replicate that for resource constrained robots? Spiking neural networks inspired by these biological neural networks offer great potential for robotic navigation due to their high energy efficiency on neuromorphic hardware, which closely mimics how the brain works. One key component for autonomous robot navigation is a task called visual place recognition, where given a query image of a place, the aim is to find a reference image of the same place from a large set of previously visited places. This is challenging as the appearance of the place can change drastically due to the time of the day, season, or weather conditions, and geographically distant places can look similar. VPR is used in tasks like detecting loop closures in Islam and global relocalization for mobile robots. In this work, we use SNNs, which translate information through binary spikes, unlike DNNs, which rely on continuous activation values. While DNNs deliver state of the art results across many tasks, their high energy usage can be a challenge for resource constrained robots. In contrast, SNNs are generally more energy efficient and have lower latency, making them an attractive option for robotics. Spiking neural networks are part of the neuromorphic computing field, which mimics how the brain works. Neuromorphic hardware enables high energy efficiency and low latency through asynchronous event based computation with independent parallel neuron processing. Though still in early stages, there is a growing interest in advancing these tools, especially for robotics, where they show great potential despite limited use cases. Our contributions include independent SNN modules that learn a small set of geographically distant places from the reference database. Our modular SNN combines predictions from all modules in parallel, enabling scalability to larger environments. We also present ensembles of modular SNNs, where multiple networks learn representations of the same place, enhancing network accuracy compared to a standalone modular SNN. Lastly, we apply sequence matching, which uses consecutive images to improve robustness to appearance changes. Our SNN module architecture consists of three layers: input, excitatory, and inhibitory. In the input layer, the images are converted into Poisson distributed spike trains using rate coding. The neurons are modeled using the leaky integrated fire model. The weights from the input to the excitatory layer is learned via the unsupervised spike time dependent plasticity. This work builds on our ICA 2022 paper with key improvements. We have eliminated the calibration process used for hyperparameter tuning and streamlined the hyperparameter selection. This makes our approach more practical as we do not need to find corresponding places between reference and query sets for calibration. We now train using just one reference set without pre training compared to two sets used previously. We also demonstrate that our approach scales even further, going from 2,700 places in our previous work to datasets with up to 27,000 places. Compared to conventional VPR techniques, our ensemble of modular SNNs achieves competitive performance average across all datasets. With sequence matching, our ensemble approach achieves the highest recall at one improvement on average, as we can see by the height of the red vertical bar. We also demonstrated a proof of concept deployment of our modular SNN on a robot running in real time on a CPU as it traversed a 100-meter path. We collected reference images at 1 Hz and trained 4 SNN modules offline. During inference, the robot moved along the path, collecting images at 1 Hz, and performed place recognition online. Our system achieved a recall at 1 of 75%. We also looked at the contributions of each component of our approach. Our prior non modular approach failed catastrophically, while our modular SNN outperformed it. Using an ensemble of 5 modular SNNs improved recall at 1 by 6%, and with sequence matching, the recall at 1 increased by 17%. Our ensemble approach with sequence matching obtained 2.5 times relative improvement compared to the modular SNN. Next, we looked at sequence matching responsiveness. We defined the term correct match sparsity, which is the mean of the distances to next correct match across all queries. Generally, within similar sparsity, the points belonging to our modular and ensemble approaches have a higher ratio than nearby data points, indicating higher adaptability to sequence matching. And methods with higher correct match sparsity show a higher responsiveness to sequence matching. And this holds for all datasets. Lastly, we studied how much ensembling helps. Our ensemble of modular SNNs consistently outperforms the mean recall at one of its members. In contrast, GCL ensemble obtains minimal gains over its members, and APGEM ensemble performance matches or falls short of its best performing member across all datasets. For future work, we will explore a few promising directions. These include making our system more tolerant to viewpoint changes, using event streams as input data, deploying it on neuromorphic hardware, and integrating it into an SNN-based SLAM pipeline. Thanks for listening. Please feel free to reach out and give our code a try.